Okay, uh, we continue with the inductive transducers. So far, we learned that the inductive transducers, there are several types. Many of them have academic interest. If you're really looking for a commercially available transducers, uh, the one that you can get is the variable reluctance. Right? Most importantly, it's called push-pull type variable reluctance. Then you have linear variable differential transformer. In the push-pull type transducer, you have two inductances L1 and L2. One L1 is increasing, L2 will decrease, and that is why we call this as a push-pull. And this happens because the reluctance of the magnetic path varies. Actually, it's inversely varies, right? So if you have two such inductances, you can put them in a bridge, right? And excite the bridge, right? So one is increasing, the other one is decreasing. Okay, it should be the other way around. It doesn't matter, you will get a negative output, that's all. So this is increasing and this is decreasing, right? So we can have this bridge. This is quite old method because again we need an instrumentation amplifier here. The differential inputs has to be right, and then you need an amplitude demodulator because the output will be a carrier frequency modulated by whatever you are trying to sense, right? On the other hand, if we look at Lvdt, the Lvdt is very popular transducer. Again, myriads of applications. Primarily, it's a linear or angular displacement sensor. This is X. So I have E1, E2, and this is E primary excitation. Right? Here again, we'll have to give an output, and we put the dot point such that the secondaries oppose each other, and we saw that this output with respect to X, so this is plus X is up, minus X is down. So we will get a voltage like this. There will be a residual voltage. So one way is to use the rectifier. We do not use a normal rectifier, even though I put the normal rectifier and showed it to you, because design becomes very complicated since the diodes have a cut-in voltage of about 0.7 volts. So what we do is we put a full wave precision rectifier, and again we put dot point is here, another full wave precision rectifier, then we give these to the subtractor, right? The output again has to be amplitude. No output is, once you rectify you have DC, so that's the DC. You will get an output which is right. So let me put this as this is plus, this is minus. So you have to design a subtractor and subtract these two voltages. This circuit is used quite a bit, but what is very popular now, if you buy a different Lvdt transducer, because you can buy only the Lvdt and you can design your signal conditioning, or you can also buy a combined Lvdt plus signal conditioning circuit. In such a case, what signal conditioning will be used, so called PSD, and in the last class we saw there are two types of PSDs. What we saw in the last class is called multiplier type phase sensitive detector. So we use a multiplier, as the name indicates, analog multiplier, right? And the output we put an integrator. Even though I put an integrator in the block diagram, what is integrator in the Laplace domain is 1 by s, right? Now I can make this is approximately equal to 1 by s plus tau. This is a first order low pass filter with a time constant of tau, and if I ensure that tau is much less than s, this I can say it is approximately 1 by s, right? So we can approximate a low pass filter as an integrator. So because building analog integrators are really problematic. The biggest problem is if I have nothing at the input of the integrator, the output is a linearly rising output I will get, just because I can't get exactly zero input, even if I have 1 microvolt input, and that 1 microvolt will slowly getting integrated, right? In 1000 seconds it will become 1 millivolt, in 1 million seconds it will become 1 volt, right? So and of course 1 microvolts is a very small voltage. So if I have this as root 2 V1 cos omega t, it doesn't matter, I can use cos omega t or sin omega t. I derived with sin cos omega t, but you can use sin omega t also. The difference is just they are 90 degrees apart. If I give root 2 V1 sin omega t here, V2 sin omega t here, E0 would be V1 V2 cos phi, right? This is what we derived. Instead we call this as in-phase PSD or IPSD. If I take the same multiplier, I give root 2 V1 sin omega t plus phi, and I give root 2 V1 cos omega t, and I put an integrator. The output E0 now would be E0 equal to V1 V2 sin, right? So because the output is sensitive to the phase angle between the two inputs, these are called phase sensitive detectors. They are also sometimes called synchronous detectors or synchronous demodulators, because I am detecting an output in synchronous with the second input, one input with the second input. The multiplier type PSDs are not very popular, mainly because analog multipliers are complex circuits and they don't give you very good performance. On the other hand, the second type of PSD is known as synchronous switching type So we take root 2 V1 sin omega t is 5, right? And we put an inverter -1. Now we put a switch, that's why it is known as a switching. So this is single pole double throw switch, and the output of the switch, I put an integrator and I get input, right? And I have the other input, I call it as sin omega t. We call this as an input and this as a reference. It doesn't matter. That input is simply put through a comparator, right? And the comparator controls the switch. In fact, if you look at this with the multiplier, you see it's quite simple. All I need is inverting unity gain amplifier, one comparator, one single pole double throw switch, and a low pass filter, right? Integrator, as I already told you, is nothing but a low pass filter. So the implementation is quite simple, right? And let's see how we get the E0. Let me look at the waveforms. Let's say this is my input, this is V1, and this is V2, right? Okay, so I have V1 and V2, both are sin omega t. Phi is 0, right? In this case, phi is equal to 0. Okay, so if I look at the output of the comparator, this is V2, right? If I look at the output of the comparator will be positive saturation plus VCC and negative saturation on the input is. So it will be something like this. Let me take it this way. Okay. So if I look at, I call this as E switch. So if I look at the E switch, when the comparator output is positive, the switch will be in position 1. When it is negative, it is in position 2. So when it is in position 1, I will get V1 as such, right? When it is in position 2, I will get minus V1. What do we see? We have a full wave rectifier, right? Now the same thing I will draw it here. I have one is sin omega t, the other is, let's say, cos omega t, right? So we so this is V1, this is V2. So the V switch will be the same. Half the cycle it will be plus half the cycle, and the switch will be in position 1 here, position 2 here. So if we look at the output, so up to this, the cos omega t term will go like this, and here it will be inverted, so I'll get this signal like this. So if I take this to an integrator, what does the integrator do? Area. So there is a positive area here, there is a negative area, positive area, negative area, they will be exactly equal because it's a cosine signal flipped at half its cycle. So E0 would be 0. Here E0 would be 2 root 2 V1 by 5, right? It's a full wave rectifier. I am not deriving what is the output of a full wave rectifier. It is 2 Vm by 5, where Vm is the maximum voltage, and in our case maximum voltage will be root 2 V1. So I will get V0. Okay. So, but is it possible to right? Um, Mathematically derive it, right? So if I look at the output of the comparator, this output of the comparator, whenever sine omega t is, whenever its input, let's not put sine omega t, whenever its inputs is positive, it is going to be 1. If input is positive, it will be in position 1. Or I would have the V in directly going, so I am multiplying by 1. If the input is negative, this is going to position 2. This is multiplied by 1. This I can call it as multiply by minus 1. Because when the switch goes to position 2, what happens? Right? If it is in position 2, I am going to get minus V1. So which means minus 1 into V1. Right? That's all. So now I can say the output of the switch, right? E switch is equal to root 2 V1 sine omega t plus phi into the signon function of root 2 V2 sine omega t, right? What is the signon function? The signon function, if I have x, is 1 for x is equal to greater than or equal to 0, equal to minus 1 for x less than 0, right? That's the signon function. So now I can write E0 is equal to 1 by t integral 0 to t root 2 V1 sine omega t plus phi into signon function of root 2 V2 sine omega dt. So this I can write it as 1 by t. Whenever sine omega t is positive, this will be plus 1. What happens when that would become positive? So it will be 0 to t by 2 root 2 V1 sine omega t plus phi into 1, because signon function in 0 to t by 2 will be 1. Okay. Now I have the second half t by 2 to t. What happens? I still have my input root 2 V1 sine omega t plus phi into minus 1, so I put the minus, right? So I can evaluate this. What is this? 1 by t. I will take this root 2 V1 outside, root 2 V1 by t, and if I integrate sine omega t, I will get minus cos omega t. Am I right? If I integrate sine omega t, I am going to get minus cos omega t by omega. So omega will be at the denominator. So I am going to get minus cos omega t 0 to t by 2. Sorry. Right? Again, this is minus this again. Sorry, cos omega t plus 5, right? 0 to t. So I will get here minus root 2 V1. I have already taken it out, right? So minus cos omega t plus 5. Again, by omega I have taken it out, t by 2 to t. right? This will become plus, right? So I will put root 2 V1. What is omega? Omega is 2 pi f into t. And what is f? F is 1 by t. So I can now cancel t by t and t. So I have divided by 2. And here I put t by 2. What is t by 2? Omega t equal to pi. T equal to 2 pi. Omega t will be pi. So that would be cos pi plus phi will be minus cos phi. There is already a minus, so I will get cos phi. Now I apply, this is, I have put t by 2. When I put 0, it is minus, because whenever we put the lower order, we have to put minus. So there is already a minus, and when I put t equal to 0, it becomes cos omega t becomes 0. So cos omega t plus t will become cos phi. Here again, when I put 360 degrees, again 360 and 0 are the same, so I will get cos phi. Now when I put t by 2, I have to put minus because I am using the lower case, and I put t by 2, I will get one more minus, so both will compensate. I will get cos. So all the terms will right. So this is root 2 v1 by 2 pi into 4 into cos phi. So this becomes 2. So I get 2 root 2 by pi v1 into cos phi. Right. This is exactly what we got when we put phi equal to 0. Right. If I put phi equal to 0, I will get 2 root 2 v1 by pi, fully rectified. So this also gives an output which is proportional to cos phi and the magnitude of the input, right? So we because we use a switch, and we switch the switch into position 1 or position 2 synchronously with respect to another input. The name synchronous switching type PSD has been put for this particular circuit. Again, instead of I take the input, I put -1, I put root 2 V1 sine omega t plus phi, and I have comparator that controls the switch. I put an integrator, and integrator, and here I put root 2 V1 cos omega t. Right? I am not going to derive it. Please derive it. The output will now become 2 root 2 V1 by y sine phi. Right? So if I give, we call this as the input in the synchronous switching type, and we call this as reference. If I give a reference which is in phase with the input, I can again replace sin omega t, cos omega t, interchange. It will work the same way. Okay, so I will get V1 cos phi or V1 sin phi depending upon what reference I choose. Right. So when we put the PSD, this is synchronous switching type PSD. So I have the input, I have the reference, I have the output. Okay. So if reference is not phase shifted by 90 degrees, I get in phase PSD. and the output is proportional to cos phi. If I put 90-degree phase shift in reference 0-degree phase shift, reference 90-degree phase shift, I get quadrature PSD and output is proportional to psi. Right? So the biggest advantage here is assume my input is root 2 V1 sine omega t, and I multiply, I put another, my reference is root 2 V1 sine omega 1 t, right? What will happen? I am going to have the output as 1 by t integral 0 to t1. t1 corresponds to omega 1, root 2 v1 sine omega t, right? Minus t by 2 to t sine omega t, right? T1 by 2 to T1, right? So if I evaluate this, I will get the output is 0, right? So if my reference has a frequency omega, it will detect an output only if my input frequency is omega or integral multiples of omega. That is also possible. I can have 2 omega, 3 omega naught. But if omega and omega 1 are not related, they are co-prime to each other, they have no common denominator, then the output would be 0. And the other thing is, if I have my input and I have a lot of noise on that, then if I use PSD, the integrator that I am using, the low pass filter I am using, will simply average out the noise and get the magnitude of my sine wave input signal. So we use this a lot in communication to detect signals buried in the noise, right? And this synchronous switching type PSD is commercially available, and the name for the commercial unit, please Google search this, lock-in amplifier. What is it? Amplifier. Right? In the lock-in amplifier, you have your input, you have your reference, right? So the both are given to an IPSD and QPSD, and these two are taken, and square root of, let me call this as V1, this is V2, to a circuit which has V1 square plus V2 square, and you get your output. Okay, so if I have, let's assume this is root 2 V1 sine omega t plus phi plus let's say noise, and this is root 2 V1 sine omega t, V2 whatever it is, V reference, right? This is really not. So V1 we already know is 2 V1 2 root 2 V1 by pi cos phi, and this would be 2 root 2 V1 by pi sine omega t. So if I now put this equation, E naught, I call this as E naught, E naught equal to square root of 2 root 2 V1 by pi whole square into cos square phi plus 2 root 2 V1 by pi whole square into sine square phi. I can take the 2 root 2 V1 by pi outside. That would be square root of sine square phi plus cos square phi is equal to 2 root 2 V1. So I get an output proportional to the magnitude of the input. And as I already said, the noise will be 0, right? So when I put integral Vn would come, Vn is a noise voltage, and the noise voltage, if I average out, it's pretty much goes to 0 volts, right? So in fact, if you want to detect signals that are buried in noise, there is nothing better than a phase sensitive detector, or a synchronous demodulator, as it is called. Okay, so these lock-in amplifiers are pretty expensive. I mean, cost anywhere between 1 or 2 lakhs to almost 6-7 lakhs. They add other functions along with this, not just this, but the main circuit inside a lock-in amplifier that is so expensive is only this. So in fact, we can use this phase sensitive detector. It has been used quite extensively in instrumentation to measure quite a lot of things, right? If time permits, I will talk about applications not in sensors, elsewhere also the Psd is used. So if okay, now I have a Psd. Okay, so I have a Psd. How do I use it for the inductive sensors? Why? Because we started learning about Psds. I told you today, if you buy any commercial inductive sensor along with the signal conditioning circuit, you can pretty much expect that the manufacturer will give you a PSD, right? Unless there is some old company, old models, they still use amplitude demodulators, but today's variable reluctant type sensors, as well as Lvdt sensors, people simply use the synchronous switching type PSTs. Okay, so how do they use? We already saw that if I have a variable reluctance type transducer, we can get an output, right? And if this is L plus delta L, this is L minus delta L, we give minus V angle 0, here we give plus V angle 0, right? And the output will be proportional to delta L, right? R, so this is going to be J omega R, J omega R by J omega L, V angle 0 into 2 delta L, right? This is what we saw, right? This is one circuit. So all I have to do is please remember, if this is a sine wave, this is an inverted sine wave. Sorry, this is the other way around. This is an inverted sine wave, and this is a sine wave, right? Output also will be a sine wave, because output is proportional to V1 angle 0. The magnitude would be R by omega L into 2 delta L. right? That will be the magnitude. So what do? We give this to QPST. Can you tell me why it has to be given to a QPST? And here I put V1 and V2, right? Because remember, this is R by J omega L, right? J is nothing but one angle 90 degrees, and when I put the numerator, it will be one angle minus 90 degrees. So I will have to detect it with 90-degree phase shift. So we have to use a quadrature phase sensitive detector to get an output. Okay. So this is a very popular circuit for variable reluctance type signal conditioning. Now what happens to Lvdt? We have the primary of the Lvdt, right? We have the plunger that moves X. We have two coils. This is a dot point, so I apply primary. So what we do is we connect this to ground, we give this to an in-phase PSD, and the reference is connected with EP, right? And the output will be proportional to X, K into X. Again, when you come to the laboratory experiment, we will have one experiment to exactly simulate this. If time permits, I don't know how many experiments we can do when you come back, and that is going to decide what types of experiment you will do in the lab and get to know. This weekend I will start giving you exercises that you can at home not exercises, simulation experiments that you can do at home and at least have some experience of about transducers, right? This course, as you already know, is a lab-based course. If you don't go to the lab and actually look at the transducers, use the transducers and measure physical inputs, it's not going to really go into an understanding, right? So transducer being a practicing area, we must go to the lab and learn the nitty-gritties. Okay, so this is the two sensors. It is now already nearly 40 minutes. So if I start the next topic, I'll have to break in between. So let's complete a little bit earlier today, and I will meet you with a new lecture, and there I am going to show you how the variable reluctance principle can be really exploited to build one of a kind transducer, right? So in the next class, I am going to give you a variable reluctance type pressure sensor, right? So I need to measure P1 minus P2. As I said, pressure sensors are dime a dozen. You can buy them today very cheap. There are MEMS type pressure sensors that are not that expensive, right? and even a conventional pressure sensor is not. Now the problem comes if I want to make a sensor whose shelf life is 25 years. What do we mean by shelf life? Shelf life means that if I build a transducer today, it should work maybe for 2 years, 5 years, 10 years, right? Even if I don't use it and keep it in the shelf and I take it and use it, it should work. Many transducers will not work for 25 years. Most commercial transducers, they give you 5 to 10 years guarantee, not 25 years, right? So that's one condition. The second condition is that it has to take vibration of 20 G, right? G is acceleration due to gravity, 10 meter per approximately 10 meter per second square. So 20 G is really vigorously shaking, right? Like I mean, even if you go on a bus or a car, the vibration that you get would not be more than 3-4 Gs. And if you go on a race car, maybe you can experience 5G, right? But 20G is really pretty high. The third is, let's say I want this pressure sensor also to take a shock of 20G, right? So what is shock? What is vibration? We have x, we have velocity is dx by dt, acceleration, which is g, right? Acceleration due to dt is d square x by dt square, and shock is d cube x by dt cube. Okay, so when we talk about shock, 20G of shock, what it really means is if I throw the transducer onto the wall and it just goes hits a wall, that will be about 20G shock, and it should still work. It should be capable of handling that kind of abuse, I would say. You may ask, sir, why we need all this? Of course, you need all this if you are going to put your sensor in a military grade instrumentation, right? Because military, they just want everything to work even in extreme conditions, right? So we will look at how to design the variable electric pressure sensor that would satisfy all these conditions in the next class. So let me complete today's lecture, okay, and I'll see you next week.